So, we're going to talk about polarizers. Now, your concept builders, the two concept builders, the first page is kind of an overview review of chapter 27. It starts with Romer, talks about some stuff about light on the back side, stuff about shadows and eclipses, things like that. The second sheet is about polarizers, what we're going to be talking about today. But it's very important you read the instructions, the first part. The first part will guide you through how to do that, because they're kind of doing it in a vector way, where you break things into their horizontal and vertical components, like we did back in mechanics. So it's a little practice with vectors. In fact, in the back of the book, there is a thing about that shows the vectors. They actually use this example of the polarizers as one of their vector examples in one of the appendices about vectors. So you can kind of look through there about that. We're going to talk about polarizers. And no, we are not making things cold. And this has nothing to do with electricity. Yes, this term can be used for electricity. We talk about molecules and atoms that have a charge at either end. Polar molecules, polarization, having charge on either end, charged molecules. It has nothing to do with that. Same word, but it's a different definition. In this case, we're talking about aligning waves, the alignment of waves on that. Light waves, when they come at very different angles. Now, this is something for transverse waves, where light is a transverse wave. Polarization only works for transverse waves. You cannot polarize sound because it is a longitudinal wave. Transverse waves. But the light comes at different angles. Some of it has a vertical orientation. It has a horizontal orientation, and the cross waves, and this cross wave. So it comes all these different orientations. But we can run it through a filter that we call polarizer, and filter out all but one of those orientations. This is what a polarizer does. Now, a polarizer is basically plastic. And a guy named Edmund Land invented this. He basically took plastic and he found that if he stretched these polymers, he stretched them out, that they would block that. And he invented the Polaroid filter on that. He's also the guy who made the instant camera. Same guy. Well, the Polaroid Land Company, but it has really nothing to do with polarizers per se. It's just that was his company. It was called the Polaroid. He called it the Polaroid Land Company. All right. So, but Polaroid and these polarizers were invented by the same guy, Edmund Land. On that. Anybody need more time? So what happens? We think about this rope and through the picket fence. I have a transverse wave. Now through the first picket fence, could I make a crosswise rope go through or a slantwise? The only thing that's going to get through is one that is vertical. And when we have a second one, it's going to let the vertical through. But if we take the second case where we blocked everything except verticals, but now the second one I've turned horizontal, will the horizontal fence let a vertical wave go through? No, so it blocks it. Notice there's no wave coming out. Same idea happens with our polarizers. The first polarizer is going to take out all but one orientation. By the way, what's going to happen to all that light energy? Where does it go? What? Well, where all this light, all these other orientations that are getting blocked, it only let the vertical through. Where does all those other orientations go in that first polarizer? Where do they go? Where's all that energy go? It gets absorbed. So what would we expect the polarizer to do? Heat up, get hotter, right? Temperature will go up. There, the energy is being absorbed. Same thing happens in your sunglasses. That's why these things look dark, because this is a polarizer. It looks dark because most of the light is getting absorbed. Most of the light is coming through, it gets absorbed. Same thing happens in your sunglasses, but for a different reason, because if you don't have polarized sunglasses, but sunglasses have a thing in them called pigment, and the pigment absorbs the sunlight on that. It's what blocks it out. It absorbs that sunlight. And then when we have a second one that's vertical, it will let the light through. Most of the light, not all of it. Some of it does get absorbed. However, if I turn the second one 90 degrees, what happens? Nothing gets through. Nothing is going to get through. And so if I have my first polarizer, and you can see that little thing in the middle through there. And if I put the one on the same orientation, you can still see it, although it gets a little darker because I have two filters going in there. But if I take the top filter and I rotate it 90 degrees, it blocks everything out. Blocks everything out on that. You know, if I have it halfway, you know, some of it gets through, so varying amounts depending on the orientation. Now, come and gather around. Now, there's a weird thing about Caro syrup. Caro syrup. Corn syrup. Corn syrup. I have a little syrup there. Now, when I put it like this, still it's yellow. You guys gather around. I'll let you guys do this at first. But when I put the second one on and I start to rotate and I'm looking down into it, I'll notice that what's happening to the color?
We have to look down.
You have to look down into it. Look down on top. Rotate the filter around and look down on top of it. What's happening to the colors? Colors are changing. Steven?
Yes.
Thank you. So rotate around. Once you rotate it, once you look at it, just rotate it, look down in it, and
all right. Do that. That more dangerous.
now, why is this happening? Well, it's a property of Caro syrup, corn syrup. By the way, this is basically, you guys who like your log cabin pancake syrup, and pretty much it's this stuff with a little bit of artificial maple flavor.
Is it good?
Well, most of the things you eat is sweetened by this. This is corn syrup.
That's right.
I wouldn't,
Yeah. But thunder with.
because I don't know where that beaker's been.
Oh.
It's kind of old syrup too. Now, it's a property, this is kind of a property of this, which means somebody was really bored one day. I didn't come up with this, someone told me about this. Someone had to be really bored. But what happens here? Now, when I put it on top of the first polarizer, obviously the first polarizer is taking on all but one orientation of light. But the thing is, the Caro syrup acts like a polarizer too, for the color. But what it does, it shifts the angle of each color. Each color gets shifted around. This is kind of the idea of the third polarizer that you're going to go through in your concept builder. But each color gets shifted a different amount. Now when it's like this, all those colors hit me, so it doesn't change what I see. But when I put the second filter on, it's gonna block out everything except the whatever orientation is of the filter, so that as I move it around, the color changes because each color has a different orientation around. This is why that color changes as you go around like that. So it kind of acts like a polarizer itself on that. You know, who comes up with this? That's probably a day that someone was very bored. I don't think I would come up with myself to say, hey, you know, why if I ran corn syrup through a filter, a polarizing filter? Wonder what would happen on that. All right, so polarizers. Now, you guys actually next week you get to play with polarizers. A lot of exercise. You guys are going to get to play with some polarizers, things like that. Like sunglasses. How would you tell sunglasses were polarized? Say you had a pair of sunglasses you didn't know were polarized, but you had a pair that you knew were. Right? You have a pair. If you know you have a pair of polarized sunglasses, and you want to know, well, is this pair of sunglasses polarized? You know, I found them in a drawer. They polarized sunglasses, and if I put them at 90 degrees, it should turn black. Should turn black. If they're not, it's just going to look the same. It's not going to change any. Why do we have polarized sunglasses? Well, polarized sunglasses are for glare. And just for ease of explanation, basically glare is that reflected light that comes off the ground and water, things like that. And pretty much you can think of it as having a horizontal orientation. Well, if I have polarized sunglasses that are vertical in their orientation, what's going to happen to that horizontal light? It's not going to get in, right? It's going to get blocked. That's the whole idea behind polarized sunglasses, is to block out glare. It's a little more complicated than that, but you get the gist of the idea of what's going on there.